Guys, in this video, we will discuss about that how can I find the Jacobian of a multivariate function. So first of all, we have to know that what is Jacobian. Actually, Jacobian is the determinant of first order partial derivative. So now let us explain about the Jacobian. Suppose if we consider three functions u, v and w, and where u, v and w, these three functions are also functions of x, y and z. That means here x, y, z are independent variables and u, v, w are dependent variables. Then their Jacobian can be represented as, actually Jacobian is defined by j, and j is equal to del u del x, del u del y, del u del z, del v del x, del v del y, del v del z, del w del x, del w del y and del w del z. Whereas here the total number of independent variable is 3 and the total number of dependent variable is 3. So here we have to remind that for the Jacobian, the number for finding the Jacobian of a multivariate function, there must be the total number of independent variable is always equal to the number of dependent variables, and the number of independent variables or number of dependent variables is always equal to the order of the Jacobian. So now I will discuss about some properties of Jacobian. So now go to the first property of Jacobian. So what is the first property of Jacobian? That is, if u and v are function of xy, then we can say that del uv del xy into del xy del uv is equal to 1. That means if we consider it like j, and del xy del uv is j dash, then we can say j into j dash is equal to 1. And sometime we have to use this property to find the Jacobian of some function. So I will show you one problem here, that if x is equal to uv and y is equal to u plus v divided by u minus v, then find del uv del xy. So see here from this equation, that is del uv del xy, means we can write del u del x into del u del y, del v del x and del v del y. So now, but see here that from this equation, that the explicit value of u and v in terms of x and y, that is quite difficult, but it is quite possible to find the del x del u, del x del v, del y del u and also del y del v. That means we can easily find the Jacobian of, that is of the form that is del xy del uv is equal to this part. So now try to find the Jacobian del xy del uv from the given relation, that is x uv. That means we can easily find del x u and del x del v, that is del x del u is v and del x del v is u, and since y is equal to u plus v divided by u minus v, so from here by using the properties of using the property of division property of derivative, we can easily find del y del u, and if we find it del y del u, we can find the value is minus 2b by u minus v whole square, and similarly we can find the del y del v by using same property, the value is 2u by u minus v whole square. So now the question is that we have to find del uv del xy. So we can find del uv del xy by using this property, that is del uv del xy into del xy del uv is equal to 1. Already we find the components of del xy del uv, that is, so now from here we can write that del uv del xy into the value of that is the del x del u is v, del y del x del v is u, and del x del v and del y del v. So we put here, and if we calculate it, we get the value that del uv into del xy is into 4uv by u minus v whole square is equal to 1. And from here we can easily find that del uv del xy is equal to u minus v whole square by 4uv. So this is the application of first property. So now I am going to the second property of Jacobian. So what is the second property of Jacobian? That is, if u, v are the functions of r and s, and also r and s are function of x and y, then the Jacobian, that is del uv del xy, is equal to, we can write del uv del rs into del rs del xy. So now I will show you one problem about the second property, that is, find the value of the Jacobian del uv del r theta, whereas the given functions, that is u is equal to x square minus y square, v is equal to 2xy, x is equal to r cos theta, and y is equal to r sin theta. So del uv del r theta means, from this question, that here we can write that del uv del r theta means del uv del xy into del xy del r theta. And from the given properties we can easily find the del uv del xy and del xy del r theta. Actually, del uv del xy mean, we can write it del u del x and del u del y. This is del v del x and del v del y into del x del r into del x del theta into del y del r into del y del theta. And see here that since u is equal to x square minus y square, so we can find del u del x, that is 2x, del u del y minus 2y, del v del x 2y, del v del y, del v del x 2y, sorry, del v del y 2x, x is equal to r cos theta, so del x del r cos theta, del x del theta minus r sin theta, y is equal to r sin theta, so we get del y del r sin theta and del y del theta r cos theta. So we can put all this value here, and so after putting this we will get this, that is 2x minus 2y, 2y 2x, cos theta minus r sin theta r cos theta, and after simplification we will get 4 into x square plus y square into r cos square theta plus sin square theta, and whereas we get 4r into x square plus y square is equal to 4r into r square, since x is equal to r cos theta and y is equal to r sin theta, and after simplification we will get the value 4r cube, and this is the value of del uv del r theta. That means we can find the value of uv in terms of r and theta. So now I am going to the last property of the Jacobian. That is, the third property of Jacobian say that if u, v and w are said to be linearly dependent if that the value of the Jacobian is equal to 0, are said to be linearly dependent, or u, v, w are not linearly independent. So here I show you, that is, here one question is given that show that the functions u is equal to x plus y minus z, v is equal to x minus y plus z, and w is equal to x square plus y square plus z square minus 2yz are not independent. That means we have to find that del uv del xyz is equal to 0 and find the relation between uv and w. So here that is given u, v and w. So from here we can easily find del u del x, del u del y and del u del z. So we get del u del x1, del u del y1, del u del z minus 1, del v del x1, del v del y minus 1, del v del z1, del w del x 2x, del w del y 2y minus 2z, del w del z 2z minus 2y. And since they are not independent, that means we have to find, or we have to show their Jacobian value is 0. So del uv del xyz means this is the Jacobian form, del u del x, del u del y, del u del z, del v del x, del v del y, del v del z, del w del x, del w del y and del w del z. So now if we put all this value, already we find here, that is, if we put here, that is 1 1 minus 1, 1 minus 1 1, 2x, 2y minus 2z and 2z minus 2y, and then if we give the change, or that is c3 dash is equal to c3 plus c2, we will get one column is 0, and by the properties of determinant, if one column or one row is 0, then their determinant value is 0. So this value will be 0. So now we can say u, v, w are not linearly independent. So now we have to find the relation between u and v. So now see here, if we find u plus v and u minus v, then we will get u plus v is equal to 2x and u minus v is equal to 2y minus 2z. And now if we squaring and adding both, we will get u plus v whole square plus u minus v whole square is equal to 4 into x square plus y square plus z square minus 2yz. And this is the value of w. So we get 4w, and u plus v whole square plus u minus v whole square is equal to 2 into u square plus v square, and after simplifying we will get u square plus v square is equal to 2w. This is the relation between uv and w. So we can say that u, v, w are not linearly independent, and they are internally, or they can dependent to each other by this relation u square plus v square is equal to 2w. So I hope you understand the how to find the Jacobian and the properties of Jacobian. So thank you.